Let's look at the West African rainfall. The main message here will be that it is strongly related to the Indian summer monsoon, especially because of this PV advection and the easterly jet that's going around the Asian monsoon gyre that we talked about with a PV minimum and crossing right across into the Atlantic sector. And we also saw the rainfall distributions for summer and winter months, boreal summer and winter months. The distribution of rainfall is pretty close to the equator, obviously moves southward during the winter months, but you can see that there is higher pressure towards the north, minimum here where we had the westerlies, and then increasing across the equator towards the south. We don't want to worry too much about this. We are mostly worried about this, and the challenge is to explain the relation between the easterly jet, the low-level westerlies that we had looked at in terms of the cross-equatorial pressure gradient, the absolute vorticity line, and the shear that is needed to balance the vorticity, which can explain the strong westerlies. And there is a relation. We talked about the Atlantic Nino and the cold warm patterns that can get set up, which can affect the interannual variability and decadal variability of the Sahel rainfall as well. As we saw before, the variability here is strong on decadal time scales. Okay. To do that, we take a simple system that we had in chapter 2. We are looking at the momentum equation, the F equals ma equation, and rewriting it. So we're going to go after the influence of the easterly jet stream on the West African precipitation, and we will look at a beta plane centered on some latitude phi0 of the equator. So writing that equation out as del v tilde del t plus the advection term v tilde dot grad v equals minus grad phi. As usual, we use the hydrostatic and equation of state to rewrite this equation in terms of the beta plane here, the Coriolis term, and we split the total velocity into a geostrophic component and an ageostrophic component, in which case it allows us to look at the acceleration of the geostrophic component entering the easterly jet on the Bay of Bengal side and exiting on the Atlantic side, and see how that acceleration produces a ageostrophic component, which is related to the meridional cell or circulation needed to explain the off-equatorial rainfall over Guinea and Sahel. So writing that previous equation with V equals VA plus VG, we get the time derivative of the geostrophic component. Remember, geostrophy is a steady state approximation, but in this case we have split the total into geostrophic and ageostrophic component, which allows us to define acceleration of the geostrophic component in terms of the advection term and the divergence term and the pressure gradient term and the Coriolis terms and so on. We can just simplify it and with the geostrophic balance by definition given as the balance between the Coriolis term and the pressure gradient term. So with the split we can still maintain this relation, and once again remembering that the geostrophic component is going to be much stronger than the ageostrophic component. So then dvg dt is approximately equals minus grad phi minus, this is the geopotential of course, minus k tilde cross f0 v tilde a geostrophic minus k tilde cross beta v vg. We can set beta equal to 0 and then work on an F plane to simplify this equation as V tilde A is 1 over, so that goes to 0. This term goes to 0, so we are just going to, this goes to 0, this goes to 0, so we're going to just balance the ageostrophic component with the acceleration of the geostrophic component. So then V tilde A geostrophic is given by 1 over F0 K tilde cross dg V tilde G dt. So if there is an acceleration of the geostrophic component, it's going to create a perpendicular ageostrophic component, and it depends on the direction of the acceleration and deceleration as the flow enters the easterly jet and exits the easterly jet. It's really that simple. So make sure you understand this simple depiction. Reminding ourselves of what we saw before in terms of the June, July, August divergent velocity field. So we had cross-equatorial flows in the meridional converging into the heating region, with vertical flows in the heating region, with the downwelling or subsidence on the equatorial side and the Hadley cell component on the other side in terms of the pressure, vertical velocity in the pressure coordinate, and the divergence, which gives us the divergence convergence doublets, which we had argued are important for balancing the cross-equatorial pressure gradient related advection of the absolute vorticity line. So you can see the absolute vorticity line is clearly shifted to the north, which is required to also explain this westerly winds in the low latitude western Atlantic Ocean that is required now to explain the rainfall that we are trying to explain. So these are just the background we had already done in chapter 13 in terms of explaining the near equatorial precipitation distributions, where we had written the velocity in terms of the divergent and the rotational parts, and we had written the vorticity equation in terms of the advection, the stretching term, and the vorticity dissipation term. And the main thing we are going to look for is how the vorticity stretching term is advection term across the equator is going to give us the dissipation term, that the meridional shear that is needed to explain these westerly winds. Okay, so just revise those parts again in case I'm going too fast, but the physics of this is very interesting. So here is our easterly jet going right across from the Indian Ocean monsoon region into the West African region. Impacts of the large monsoon heating over South Asia. I don't know what this noise is. They are probably spraying the disinfectant for mosquitoes, toxic stuff that gets sprayed to kill the mosquitoes, but you have to be careful that you also don't get killed. Okay, the upper tropospheric circulation is shown in terms of the easterly jet. Note the extent of the easterly jet that commences over northeastern Indian Ocean and extends out across the Atlantic Ocean. Magnitude of the westerly wind component is easterly wind component is color coded red. Okay, so there is the westerly component down here. All the typos and errata. The secondary circulation associated with the entrance and exit region of an easterly jet is shown here. So a parcel of air, let's say, that's entering the westerly duct over here is going to accelerate because of this squeezing of the pressure gradient and the related geostrophic acceleration. And by this equation, by this equation, acceleration of the geostrophic component is going to give us a geostrophic component, which is easier to see here. So you're going to have a divergence and convergence on this side, which is going to actually give us more rain on the Bay of Bengal side, and then you're going to get a meridional circulation of the geostrophic component on the exit side, as the geostrophic flow that is exiting is going to decelerate. So there is the acceleration here providing a southward geostrophic component, and the deceleration of the geostrophic component here giving us a northward geostrophic flow, again remembering that this is much smaller than the geostrophic component. Okay. Note that the geostrophic flow produces a northward deflection of the winds that is consistent with subsidence on the northward side. So there is convergence and divergence doublets that we talked about in terms of the cross-equatorial pressure gradient, so that is still there. But you're going to get subsidence on this side, which is going to explain the near equatorial distribution of the rainfall in the West African Guinea and Sahel regions. Okay. On the northward side, you're going to have subsidence and rising pressures, surface pressure, which I had shown before with the minimum in the Guinea coast region. Okay, the letterings denote the cross sections through the entrance and exit regions of the jet, and divergence, convergence denote upper tropospheric divergence and convergence from the geostrophic winds. Geostrophic winds, of course, are non-divergent. Schematic diagram of the induced secondary circulations are shown here as cross sections AB and CD. So V bar G, V tilde G, V tilde A represent the geostrophic and geostrophic component of the velocity respectively, and PI correspond to the pressures. Okay, so here is the meridional direction going from equator to North Africa and equator to north of B. So we're talking about north of B here. This is the CD section and the AB sections. So you have rising motion on this side, subsiding motion on the northward side created by the now it's the chopper. West Africa is not well blessed with peace and quiet, right? So that is our meridional circulation, which explains this easterly jet in the middle and the geostrophic acceleration, whereas on this side you have rising motion north of the Bay of Bengal. So you're talking about Bay of Bengal here. Rainfall is going to increase and subsidence on the equator. So this is the basic dynamics of the West African rainfall. You can just think of that as a part of the IPCZ dynamics, but when you want to actually look at the details of the dynamics, you have to remember that it's very closely related to the easterly jet from the South Asian monsoon region all the way from Northeast India into the Atlantic. The relation on interannual timescales is shown here in terms of maximum 850 hectopascal zonal winds versus the latitude of absolute vorticity being 0. That relation is pretty high. So as the vorticity line moves latitudinally based on the SST gradients associated with, let's say, something like the Atlantic Nino. So the equatorial temperature and the Gulf of Guinea temperature, for example, there is a high correlation with the westerlies, which basically means the rainfall. So relationship of wet and dry Sahel rainfall years. A is the strength of the 850 hectopascal westerly winds north of the equator, plotted as a function of the location of the zero absolute vorticity contour. And in B, we are looking at strength of the 850 hectopascal westerly wind north of the equator, again plotted as a function of magnitude of the cross-equatorial pressure gradient. Red and black circles denote dry and wet years. Correlations are highly statistically significant at 0.70 and 0.84 respectively. So the absolute vorticity line, the cross-equatorial pressure gradient, the dynamics that drive the near-surface westerly winds, the easterly jet dynamics, the geostrophic winds giving us the meridional circulation, etc., are all dynamically related to each other, and they determine the multi-decadal variability of the Sahel rainfall, which is related to the 850 hectopascal winds. Sounds complicated, but just please read and make sure that you understand the simple dynamics we are explaining, both for the Tibetan plateau heating role in moving the rainfall so far north over India, and the easterly jet associated with the PV advection from the extratropics into the tropics, across into the Atlantic with the easterly jet, and how the easterly jet and the geostrophic acceleration is giving us enhanced rainfall over the Bay of Bengal and reduced rainfall over Sahel. Okay, simple stuff, very important and interesting stuff as well.